Good afternoon, everybody. I'm Tom Woodfin. I am the Director of Development for the Data Platforms team at InterSystems. We build InterSystems IRIS. You may have heard of it. I'm going to take you today on a deep dive into the inner workings of IRIS, show you how we build it to scale for your most demanding applications. This is going to be deeply technical. I'm going to cover a lot of ground quickly. So buckle in, and please hold any questions for the end. Oh, now it didn't work. All right. This. So quick roadmap for the session. I'm going to talk briefly about the IRIS data platform, why I think it's different, why I think it's special, and then transition into some ongoing adventures in scalability. So our partners succeed and grow building on InterSystems IRIS, and we really have to race to keep up. And then I want to talk about specific areas of investment that we're making to continue that profitable adventure in scalability. And I will go through some of the recent returns we've seen in recent and upcoming IRIS releases. So the IRIS data platform. People ask me, what is IRIS? What makes it different? And I think the way I think about it is that it's really two core components. They're both secure, they're both flexible, they're both scalable. It's a multi-model data engine and a general purpose software runtime. And it's really the fusion of these things that enables applications at scale that really just wouldn't be possible on any other platform. If you think about a traditional database application architecture, you've got an application server that wants to get some data from the database, so it composes a SQL query, puts it on the wire, sends it to the data server takes the query off the wire, runs the query, produces a result set, sends it back over the wire. So at best, this is like a milliseconds class operation. And IRIS is really different. IRIS has this general purpose software runtime fused into the data engine. So you have application code, whether it's Python, SQL, C++, or of course ObjectScript, that can reach out and touch and manipulate persistent data on the scale of nanoseconds. And that's really what makes it different. So the IRIS architecture was built to enable high-scale, data-intensive applications. I'm going to take you on a deep dive into specific work we've done on a few of those key scalability technologies. ECP, Enterprise Cache Protocol, is the first one I'm going to talk about. It is really the key technology for scaling compute horizontally with InterSystems IRIS. So we really need to understand what its limits are. And we did some work with one of our most high-scale application partners in their scalability lab. They have a reasonable approximation of their application load in the form of a benchmark. And we really wanted to see how far we could push that benchmark. So they went and begged and borrowed and stole as much hardware as they could find, and ultimately built a ECP cluster composed of 100 ECP application servers, in aggregate more than 4,000 CPU cores. So what do we do once we've got this set up? Well, we start turning the dial. We turn on that application load simulator. We turn it up, we turn it up. As we turn up the load, we see throughput go up. We keep turning up the load. We keep turning up the load to extreme levels. At some point, far more extreme than anything we've seen in a real-world application, we see that throughput start to level off. We're adding more load to the system. CPUs are at 100%. More load is on the system, but more throughput isn't the result. We've stopped doing additional work under additional load. And then we dive in, see what's going on. So what we're really looking for is points of serialization. And this goes back to a very old idea in computer science called Amdahl's law. And what Amdahl's law says is that the scalability of a parallel system, like InterSystems IRIS, is ultimately constrained by the amount of work you have to do in serial. And one of the most common areas of serialization inside the InterSystems IRIS architecture is around what we call resources. Resources are a highly optimized form of mutex, and they're used to protect access to critical sections of code and data in the InterSystems IRIS database. So resources are what they're there for, is to guard against race conditions. That's a case where you've got two processes running at the same time, making inconsistent or colliding updates to a data structure. And they can do that. If they do that in the wrong way, that data structure is effectively broken, its preconditions no longer hold, and you've got a corrupt system. And here we've got tens of thousands of processes simulating a workload, and some of these resources guarding some of these critical sections are getting a real workout. So we've developed profiling tools at any number of different layers, all the way up from application code down to these very low-level mechanisms to trace system behavior. And in this case, the one we wanted to look at was a counter called nseizes. So what a seize and nseizes represents is that a process wanted to acquire a resource, but another process was holding it, so it went to sleep and waited for that resource to become available. And of course, while a process is asleep, it's not contributing to your throughput. It's just sitting there. If anything, it might be costing you a little bit of your throughput because it wakes up every so often to see if that resource is available, and under heavy contention, it's going to be waiting a lot. So we looked at these numbers, and we saw this particular resource, this ECP SWork resource, really sticking out like a sore thumb. Now, what the ECP SWork resource does is it protects the ECP work queue. So all operations that are done through ECP from a client to a server, whether it's writing a global or taking out a lock, those are all put into a common work queue, which workers then pull tasks, write a global, take a lock, off of that queue. And we could see that, the resource that was designed to protect that queue was under heavy, heavy contention. This is not the first time we've run across a resource in contention. So we've got a nice bag of tricks that we can use to try to improve the situation. One way to think about Amdahl's law is that if you're constrained by how much work you're doing in serial, well, do less work in serial. So we looked at the section of the code that was running in the most common uses under this resource in the most common cases, and looked to see how we could shorten it. Make it do less work while that resource is being held so it can be freed and released for another process to acquire. We also have the ability to take a resource like this that we expect to be under heavy contention and change its implementation to use atomic instructions, so-called lock-free algorithms, which handle that kind of contention much better, perform much better under that load. And finally, we noticed that some of the amount of work that was being done while holding this resource was actually touching a very different part of the data structure than the most common cases, the bulk of the work that was being done. So what we did was we could split off and create a new resource, this ECPS backobj resource, and we could direct these specific tasks, some fraction of the work, to use this resource, and then you can have two processes at the same time, one that's touching one part of the structure and another that's touching the other. And this got us some relatively easy wins, which we were able to validate immediately. In a second, I'll show you what the net gain of those were. But we really knew that there were more fundamental improvements possible. So another way to think about Amdahl's law is that if you're constrained by the amount of work you're doing in serial, take some of that serial work and make it parallel. And that's exactly what we did here. So we replaced a single ECP work queue structure with multiple lanes of a multiple dynamically sized set of lanes, replacing that single choke point for scalability. And we think now that really it's unlikely that we could acquire in any reasonable in any reasonable sense, acquire enough hardware to build out a cluster that would actually bottleneck here again. So we've effectively eliminated this particular bottleneck as a constraint on scalability. And this really is a win along a couple of dimensions. First, it allows you to scale to serve more customers and scale on the same amount of hardware. And second, it also gives you the freedom to make your applications more data intensive, to use more resources, to do more work in service of your users. This is a chart of the improvements we first were able to measure, and secondly, we think we would get if we actually could accumulate enough hardware to test it. I will admit this is a Bezos chart. The actual rates you're going to see are going to depend greatly on the particular workload you're applying and the particular hardware configuration you're running on. But it's safe to say that the unit here is in hundreds of millions of global refs, as you might expect from Terry's slide on Monday. So that was about scaling compute. Of course, if we're going to have massive scale of compute, we also need to be able to have data in there to perform that compute on, which means we need to be able to consume massive amounts of data for these high-scale applications. And the ability to load that data into our system, as well as get the data back out again, is a function of our client technology. This is sometimes referred to as XDBC. So before I talk specifically about our client technology, it's important to understand and take a deep dive into how data is represented at the very lowest levels of IRIS. Before we get there, though, I want to take a detour briefly to what should be a familiar data model, the SQL table. SQL tables are made up of rows with a row ID identifying the particular row, and those rows are made up of fields. And in row form, I'll get to the new columnar form in a moment, tables are represented in globals with the $list structure, which you may be familiar with if you've done any ObjectScript development. This is a long-standing structure in IRIS. It's highly optimized for access time and compact size. And ultimately, like most structures in InterSystems IRIS, it's effectively represented as a byte string. This is the byte string representation of the first row in the sample data we were looking at. Does anybody remember Lost? Anybody watch Lost back in the day? If you did, you may remember that there was sort of this ongoing trope of this mysterious sequence of numbers. I am not entirely sure if in 6 seasons of the show they ever actually truly gave a satisfying explanation for what those numbers were meant. I will not make you wait 6 seasons to understand the importance of these numbers, just a couple of minutes. But if you can, try to keep in your mind the first 5 bytes of this particular $list representing a row in this table, 06, 01, 41, 41, 50, because we will see them again. There we go. OK, so we know where we want to get to. We want to get to $list encoded data recorded in globals. So how do we get there? Now, traditional approaches use a generic protocol, a generic encoding of the data. So, the Postgres SQL wire protocol is very commonly used by a lot of tools that aren't even Postgres. And you can imagine having an encoding that's something like, well, we'll use the ODBC text representation of a timestamp. This is something that actually InterSystems in previous generations of our technology did. And the server gets these messages off the wire, it picks it apart a field at a time, builds its own encoding of the row, which might involve re-encoding some of these data types into the internal types used by the system. It might involve rearranging these fields because the order that the client produced them isn't the same order as they're stored inside the database. It validates them, builds secondary indexes, et cetera. All this takes a lot of CPU. So the IRIS client protocol is different. Before any data is exchanged, it performs an exchange of metadata. So the server explains to the client for the tables it's interested in, the fields are in this order, they have these types. And the client understands how to use that information in order to directly build the $list that the database wants to use as the row representation of that row data. And this is often performed. One advantage of this is you're distributing that work rather than having to all be centrally done on the server. It's distributed among these many clients, which often have their client technologies written in languages like C and Java that are really optimized for this kind of compute. So the server gets this message. It does whatever additional validation is necessary. We don't just trust the data that comes from the client, that it matches the constraints of the schema, build any secondary indexes. But really, the important thing is it avoids all this re-encoding, all this shuffling of data. It can just take this $list directly off the wire and write it into a global. OK, so do you see these numbers? They're back. 06, 01, 41, 41, 50. This is application data streaming directly into IRIS at wire speeds. So we call this particular part of the client technology fast insert, and the throughput gains are tremendous. Here we see rows per second being ingested single-threaded for 3 of the largest tables of an industry-standard SQL analytics benchmark. It's something like a 10x multiple when we first implemented this. And the cool part about this is actually the optimization is bidirectional. We have a corresponding optimization called fast select, which allows the server to deliver to the clients those rows directly out of globals without having to reformat them into the result set. And this is ideal for building ultra-high-speed data pipelines, either going into or out of InterSystems IRIS. So our columnar SQL, which I hope you've had a chance to hear something about at this conference, uses a new representation. It does not use $lists. For one thing, it uses 1 global per column. So data for a particular field is segregated from the data for other fields. And it uses this new $vector structure. So $vector is optimized for long arrays of data of the same type, and also for data that might be very similar. So, I might have declared that my field is a 64-bit value, but in fact, if all the only numbers I'm actually storing in it are between 0 and 100, the dollar vector encoding recognizes this and will only use a single byte for each one of those values, as opposed to using the full 8 bytes of a 64-bit structure. So you can see here, you can see that we record we store these dollar vectors in globals, in chunks of like 64,000 values per vector. That's what we see here. And so, all right, so we want to be able to use a similar kind of optimization in order to minimize the amount of work that the server has to do in order to ingest client data. So, what could we do? Well, one thing we could do is we could teach the client about dollar vector in the same way we taught the client about how to encode dollar lists. We don't like that solution. Dollar list has been around forever. We're not planning to change it very often. Whereas dollar vector is something that's new. We think there's a lot of opportunity for further optimization there, new encoding methods, being able to support new data types. Maybe we change how the dictionary aspect of it works. And we don't want to have to continuously keep clients up to date with that information. And really worse, we want our clients to be forward and backward compatible, which means that it may be too late to teach a client about some new thing we want to do in dollar vector because it's already out in the field. Fortunately, actually, dollar list is already actually pretty good. It's not as good as dollar vector, but it's still pretty good at storing the kind of data that we're putting inside these vector chunks. So data that's all got the same type, that may be actually smaller than its declared type. So it's and the client already knows how to build a dollar list, so it's easy for the client to build. And it's also extremely fast for the server to transcode. So the server gets a dollar list of 64,000 integers and can very quickly pack that into a corresponding 64,000 element dollar vector. So the result is we're able to do the same kind of wire speed ingest with columnar data that we can with row data. And the effect is even more dramatic because when you're updating columnar data, when you're inserting a new row, you have to update a column for every column in that row, and that just means more data shuffling. It's as if you have however many fields you have that many secondary indexes. So it's the same kind of impact on ingest performance, which means minimizing that data shuffling through fast insert gives us, in this case, I think there's something like 100x wins. You can talk to Dave Vandergreek; he's got the specific numbers. The third example I want to walk through is around raw ObjectScript performance. Which is important to you. ObjectScript is a foundational runtime for IRIS applications. I say a because now it has embedded Python alongside it. But for a long time, it was the only way to write foundational applications in the IRIS runtime. So, and it's important to us. We've built our SQL engine, our integration engine. Lots of our other technology runs in ObjectScript. So its performance really matters. And I'm going to talk specifically about a very common mechanism in any programming language, which is how do you dereference a variable? How do you go from a symbol to a value? It happens millions of times per second in just a single ObjectScript running process. So in order to sort of motivate that, I've got a small example here. This is a simple function. It's just designed to log messages. It takes a priority argument, takes a message template, it takes parameters to fill into that message template. You've probably called an API like this before yourself. Runs a little logic to say, well, okay, am I running in a diagnostic mode? If I am, then I'm going to write the message out to a diagnostic device. If I'm not, then I check the priority. I'm only interested in logging messages with a priority higher than 0, so I use a log device there and put out the message. So ObjectScript is a highly dynamic language, which means that the runtime mapping between these variables and the values that they contain is very complex and it's ever-changing. So it's a challenge to optimize that. So ObjectScript essentially has two types of variables. Private variables are what are used in methods and procedure blocks by default. Everything else is public. So there are a lot of public variables in an IRIS system, especially in long-lived code systems that have been around for quite a long time and predate the introduction of methods or procedure blocks. And you can note that this function itself is not a procedure block. So all of these variables are public variables. And the way we track the values of private variables at runtime in IRIS is through a per process symbol table. So this is a hash table. You can essentially hash the name of the variable, look it up in this hash table. The result is a descriptor, which is essentially a pointer to the value of that variable at that time. That's the important thing to understand. It's constantly changing as you run through code. And this is the core, this is the ground truth of what a variable represents at any point of execution in IRIS. So the symbol table is a hash table, as I said, and that's pretty fast. It's not so bad. But if we could directly look up, this happen, as I say, variable references happen millions of times per second. We recognized very early on that if you could look up these values in an array, that would be much, much better. So what the routine compiler does is it actually tags every unique variable in a routine with an index. So assuming this is the first function in the routine, priority gets a 1, message gets a 2, parameters gets a 3, and so on and so forth. So now we can use that as an index into a per routine cache that's a table from that symbol index to that descriptor. And this greatly accelerates how quickly you can resolve a particular variable to its value. And this is called the pfast table. And so that's a cache, right? The values of those descriptors can change over time. So we need to be able to make sure that cache stays valid. And how that used to work, we'll walk through some examples to see how that used to work, and then I'll discuss how we've improved it. So we're going to look at a couple of different callers of that log message function. This is one called process event queue. It wants to use the log message function in order to record an instance where it couldn't get a new message off the queue before the timeout expired. It has a couple of relevant variables. It's got a params array that it's passing into that log message function. And it also has a context, percent context variable, which is not uncommon. It's not an uncommon use of percent variables to maintain sort of application-specific context. As you're calling down deeper and deeper into code, you can consult that percent variable to see some context that one of your callers set more than one level up. So briefly walk through the mechanism from the symbol table to the pfast table. It's really not complicated, or wasn't very complicated. So as soon as you call into a routine, if the pfast table isn't present because the routine hasn't been called into before, hasn't been loaded before, we populate the entire pfast table using the current values from the symbol table. So in this case, we find params, we see that it's there, it's got a particular descriptor. These other variables also had values in the symbol table, though they're not affected by the particular caller. And now we can use this pfast table as we move through log message, as we encounter variables, we can quickly look them up in this cached version of the symbol table. But what about if we've got a different caller? So here we've got a method called export table, which wants to use logger for a very different purpose, log message for a very different purpose. It wants to record the fact that it failed to open a file that you asked it to export the table into. So it's got a very different context. It doesn't, in fact, have a percent context variable. It doesn't know it. There may be one somewhere up the scope, and in fact, the content of the symbol table I've used as a demonstration suggests that there is. And it's passing into that function a private variable by reference. It calls it args rather than params for those parameters to the message template. So what happens if we try to use the existing pfast table? Well, it's wrong. I mean, the code's not going to work. You're going to get the wrong results. And it might blow up, because who knows if those descriptors are actually even still valid. So the ObjectScript runtime isn't going to let this happen. It detects the fact that this table is no longer valid and blows it up. And it goes through exactly the process I said a moment ago and builds it all again using the information it has from the caller and from the symbol table. So this is a small example. OK, whatever, I had to rebuild an 8-entry table. But realistically, we've seen routines from long-standing applications that have hundreds or thousands of public variables. And this means both that there's an extremely high cost to building that table and then throwing it away. Maybe you only used a little bit of it in between calls. And it's also introduces a much greater possibility that you're going to have these kinds of invalidation problems that force you to throw it away in the first place. So it is actually surprising how often the best solution in computer science is laziness, and that's what we found here. There was a major re-engineering of the PFAS mechanism, but the fundamental idea is simple. We start with an empty PFAS table, and we only add variables that we encounter during the particular execution we're doing right now. So if you follow along with the bouncing emoji, you'll see that we're adding variables to the PFAS table only as we encounter them. So there's two benefits to this. One is you don't build what you don't use. You don't pay for what you don't use. And you also don't introduce the possibility of unnecessary conflicts. So if a variable hasn't been encountered before and hasn't been put in the PFAS table, when we find it on the next call in, we know that we've got a valid, we know that we can just populate it because we know we've got a current value. So we only saved one variable in this simplified example. That's the diag device because we took the other leg of the branch. But realistic applications, this means orders of magnitude less work. Even methods and procedure blocks also use public variables. So this isn't just helpful for sort of more pre-procedure block, pre-method code. So if you're passing an array by reference, which is a common thing, or you're using a % context variable, like in our CSP or REST APIs, this is potentially going to save you some significant CPU. So we measured this on both InterSystems applications and on some of our large partner applications, and the win is really huge. It doesn't look as huge. This chart doesn't look as dramatic as some of the other ones I've shown you during this session, but it's important to keep in mind that this is pure application workload. This isn't part of the system. This is the system delivering simulated value to users, right? This is the actual cost in CPU of delivering your application's functionality. And through a combination of changes, you can see this is an evolution. We started to do some preliminary changes to sort of, once we realized this was a scalability bottleneck. And we also, as you'll see, there's a bar here labeled application changes. Because we realized this was a problem for large, long-standing applications, we could suggest to our application partners, both internal and external, that they rewrite some key parts of their application that were causing these invalidations to use private variables instead of public variables. And the result was a really nice benefit, like something like 8%. And so, but when you get to the net conclusion of our improvements, of rewrites to code, to take advantage of those structures that can be used more efficiently, the net is like a 30% CPU win. Which really does mean like 30% less CPUs to buy for your deployment. And it also means, I think more importantly to me as an application platform developer, it's 30% more headroom for your application to be richer, to serve users better. So those were some really great wins. I'm really excited. I'm so proud of the team that pulled them together. And we want to keep it going. So to talk about the investments we're making along the scalability, I think it's worthwhile to really split it into the two tracks I talked about when I talked about the IRIS architecture, which is to say data scale, so how large a volume of data can we manage, and as that volume increases, what problems do we encounter, and also scaling computational throughput. So I'll continue those tracks along through this discussion as I talk about the investments and the results that we've seen. So on the data side, we have large operational and analytics partners that both see on their roadmaps for their biggest customers petabyte scale data, and we want to be there when they get there. That means supporting much larger databases. It means being able to support the journaling for databases at that scale. It means being able to support ingesting that data, as we saw in the fast insert example, so that you can actually build up that petabyte of data in the first place. And secondly, at that scale, compression and compaction really more than pay for themselves. I mean, if you can get 1%, 1 petabyte data set, if you can compact it so that it's 1% smaller, that's 10 terabytes, which is really nothing to sneeze at. You also have qualitative manageability challenges. One I'm going to talk about in a little bit is backup once you get to that scale, and we really need to make sure those are addressed. And finally, cloud really introduces some radical new storage capabilities, storage services, things like object stores, that just couldn't exist in an on-premises environment. And we have to think about how we can best take advantage of those. On the workload side, the ECP example was really apropos. We want to be able to coordinate workloads on systems with thousands of cores. And ECP is our technology for scaling out compute over clusters like that. So we're going to continue to be focused on it. Ever since the Moore's Law really stopped delivering single-threaded performance increases from our CPUs, the CPU vendors have really started to work around this, or to emphasize or to improve your ability to write high-scale applications and our ability to write a high-scale platform by introducing new instructions, which means you don't get the performance for free. You've got to rewrite your code in order to take advantage of them. And chief among these, I think, is the vector units, the SIMD instructions that CPU vendors like Apple, AMD, Intel have all been introducing and expanding through their generations, and we've got to be able to take advantage of those. We have to be thinking about distributing work in parallel within a host. For large-scale applications, if it's serial, it's effectively broken. And we have to think about distributing that work across a cluster. So our SQL, our integration engines have to be architected in order to scale out as well as up. I mentioned the languages we support inside the IRIS runtime. Those languages are for humans. Increasingly, computation is being, software is being written. That's really what machine learning models are. Software is being written by machine learning algorithms that are producing these models, and we want those models to have the same access, the same high performance, high speed access to the data maintained by the persistence core of IRIS as any of our other runtimes. So ML being as deeply as embedded as ObjectScript or Python. And we really have to continue these good old-fashioned shoe leather investigations of bottlenecks, the kind we discussed in the ECP example. And again, for compute, cloud is really a radically different platform. I think the most important thing when it comes to compute is the ability to elastically provision and deprovision, I think is probably more important, effectively unlimited amounts of compute capacity. And really the deprovision is important because you want to have your current scale, you want to match your scale curves with your cost curves so that you're not provisioning resources you don't need. And that involves investments on our part for sure. So some of the things we've gotten in recent releases from this focus. So we've seen you're going to see throughout these slides a continuing focus on journaling. We want to be able to journal less. We want to be able to journal smaller, and we were able to achieve that in 2022.1. For database write performance, we took a similar approach to what we did in the ECPS work example, which is to say we replaced the use of a single write daemon with a number of write daemons with a corresponding increase in write throughput. Frequently, in large-scale and small-scale applications, a lot of your data lifecycle is taking old data, killing it, or archiving it, moving it out of the operational database, and replacing it with new data. And so we spent some time figuring out how to make sure it was the case that we could kill and then recycle those blocks more efficiently. Even in the cloud, it turns out, there are still power cords to trip over. And so we wanted to make sure that our recovery times scale better for the amount of data that needs to be recovered from your journals when the system comes back up. And analytic workloads in particular are absolutely voracious for data, analytics and machine learning for that matter. So we've been focusing on taking advantage of those, using those client protocol technology to add utilities to SQL, in particular the load data utility, in order to produce high performance bulk loads through SQL. On the workload side from 2022.1, our large operational partners support systems with tens of thousands of jobs on a single node. That is a problem for the OS sometimes, but it is also our problem. And so we've been focusing on making sure that a process goes from created to running, usefully running application code in as short as time as possible. This is also where you'd see the first phase of that work we did around the symbol table and PFAST. We also improved the management of routine resources. That was something we identified as a scalability bottleneck on systems that have many thousands of routines. On the SQL front, really we have been focused on providing the SQL query processor with much more detailed information, much more detailed metadata, including histograms of field distribution, in order to enable more efficient query plan selection. Finally, in 2022.1, one of the great things about sort of owning the language, owning the entire stack of the platform, is that we can build capabilities into ObjectScript, which we then can exploit inside higher levels of the system, such as SQL. And in this case, through a combination of those heuristics and some new code generation, we are able to, for small temporary tables during SQL query processing, use local arrays instead of globals. And if you've got a small amount of data, local arrays can be accessed much more quickly. On the 2023.1, so the version, the EM version we released back in April, journaling was again a focus. In this case, we're talking about journal transfer to mirror nodes for high availability, disaster recovery, and reporting. We spent a lot of time optimizing how that data is put on the wire, how it's pulled off of journal files on the primary, put onto the wire, and then also quite a bit of focus on how it is then de-journaled, turned from journal information being transmitted from the primary into actual updates to globals on those HA and reporting nodes. We also, as you may have heard, introduced our columnar SQL support for production in 2023.1. That means the dollar vector format I discussed earlier. We also added, as an experimental feature, soon to be a production quality feature, our foreign tables capability, which again is designed to take advantage of that client technology to set up exactly those kinds of data pipelines I talked about earlier, really for, in this case, the specific goal of allowing you to integrate external tables, external sources of data with your IRIS tables as if they were local tables. On the workload front in 2023.1, you will see the initial round of scalability improvements in ECP that I discussed. This was kind of the short-term set of solutions. Continue to see improvements in ObjectScript variable reference performance. We also, this is the compute side of columnar is through a primitive called vectorop, which is basically a basket of useful SIMD optimized operations that perform things like summing numbers at rates of billions per second. And we aggregate those into what is essentially a complete rewrite of our SQL query processing engine to exploit that vector op capability, so we can be processing essentially 64,000 rows worth of data at once instead of a row at a time. We also had recognized that we needed to improve our parallel query execution architecture to account for the volumes of data we were going to see and the structures of data we were going to see in the columnar environment. So this required, actually was the work of a very smart young developer who kind of took this on as an experiment. Well, what if we tried it like this? And before we knew it, she had a full-fledged, complete parallel execution architecture that we're using to replace everything we do in parallel at the SQL layer. It's really impressive work. Upcoming releases. I put an X here. You should think more like 5 years or less than 10 years, but no promises because nothing's done until the paint's dry and it's released. But on the data side, we're really re-architecting to overcome database size limits. First, like file size limits. Most file systems these days can accommodate just about any size file you want. But even if they can, it's rather awkward to be manipulating a database as a single 100 terabyte file. So we want to make it possible for you to split up a logical database into a number of smaller physical files. We're also reworking the database format in order to raise our existing database size limits. So today, if you've got an 8 kilobyte database, that's about 32 terabytes you can maintain. We want that data set limit to be into the petabyte range, and you should see that. We're also continuing to focus on dejournaling. We're also continuing to extend the client technologies. We have this really interesting framework called Persister, which in addition to ingesting data, also adds the ability to transform that data as it's moving into IRIS. So either moving it out of your system or into your system with essentially arbitrary transformation at tremendous tremendous throughput rates. And we're also looking at sort of the next generation of our columnar technology. There we're looking at targeting time series, Internet of Things use cases. So medical devices is a primary area of interest, where we're going to be working on technologies like delta encoding, double delta encoding, and further compression schemes. And on the workload front, you will see, I believe in 2024.1, as I put on the slide, I'd be very surprised if not, that final implementation of the PFAST improvements that resulted in such significant CPU gains. We've been focused on the scaling of the use of the shared memory heap as data grows, as parallelism grows in particular. Parallel SQL is a client of the shared memory heap, and so we want to make sure it can scale effectively, both for size and volume of activity. We're also looking to extend the parallel execution architecture I talked about for SQL, not just within a single box, right, but use ECP to distribute it across a cluster. So you could take that 4,000 core ECP application server and dedicate it all to a single query. So light up a whole cluster of 4,000 CPUs with one SQL query. Or for that matter, one embedded Python program, which is pretty exciting. And finally, we're really focused on that sort of the data pipeline for machine learning. How do we move around data frames, NumPy arrays, via embedded Python as efficiently and as scalably as we can? So that obviously includes a parallel component. So thank you for sticking with me through this rapid journey, but more importantly for your continued growth and success, because it's that success that really fuels our drive to scale to keep up with you. And really, I love what I do and love what you do that makes it possible. So thank you. Any questions? Sure.
Our application used to have 2 application servers. We then went down to 1 application server, and now we're going to scale up to 8 application servers. But when we use the 2 application servers, we encounter the dollar increment ingestion. Is this still true for the current ECP?
Yes, it is. Have you investigated using $sequence?
Yes.
Okay.
No, we didn't. No.
You have. So the scalability problem you're running into is really fundamental to the semantics of ECP, right? We want to make sure that dollar increment has to be recognized across the entire cluster as soon as you make it. Commonly, what dollar increment is used for, right, is to say, okay, I need another row ID, right, or the equivalent for whatever your data structures are, right? I'm going to create a new thing and I need a new identifier for it. You can use $sequence instead, and what $sequence does is give you a chunk of IDs per process so that you can go through all those, and when you run out, you'll get the next one. That's only when you run out of your allocation automatically. So yeah. It has effectively the same semantics as dollar increment. The only thing you lose is that these might not be contiguous, right? You get a chunk, and then he gets a chunk, and you only fill in half of it, et cetera. All right, thanks everybody.